Thanks for joining me to get started with Spark on Theta. So my background is lattice quantum field theory. So Spark is my recent excursion and try to figure out whether it works for scientific applications. And I guess there are many interests among you to actually deal with a large number of nodes on Theta. So let's see. So this talk is mainly about how you get started, and I will not really go into many details. And we're actually still working on how to get the best performance out of it. So basically the talk is very simple. You only need this one slide, and I'm pretty much done. So if you just want to get started, there's 3 different things you can do. The first simplest thing is, of course, just run the built-in SparkPy example. So if it's similar as how you get started with Spark on your laptop, just run an example called SparkPy. Of course, you have to go start this command, which is script we provide to interact with the COBOL job script. So it will submit the job, and you wait some time, and it will give you back some results in the local directory in some files, output files, and you can examine all the log files under it. So yes, most of the command lines are similar to what QSub does, and for the rest, like if you want to give it a Java class, you assign a class and give a local URI because it's more efficient. So the Spark does not try to actually send the whole a couple 100 megabyte Java file over the network. As well as it also works with Pi and PySpark, in which case you just give it Pi. So in this case, I guess Spark is still sending the script.py over the network to all your nodes, but mostly it's fine. And it should also work with data frame R, but I haven't really tried that. So this is all you need to get started, but let's just go into a little bit details. So first, I should start with a little bit about what is Spark. And I guess if you don't know, then it's good to know what Spark does. And if you already know, I guess it's probably enjoyable to see this thing again. So so this is what essentially Spark does. So there's some master instances got to the application, and it will contact the cluster manager, which essentially the cluster manager manages a bunch of workers such that each worker spawns a couple of executors. So one of many executors, and each executors will receive the tasks assigned by the cluster manager, and will figure out, the driver figure out what path it does each task should do, and then the executor does them. So the whole point is it has this resilient distributed data set such that all the data are distributed to all the executors, and each task will be serialized from the driver and send it over to executor, and the executor will execute them. So if you have your HPC hat on and you look at this and you realize this is not going to scale. Why? If you have a bunch of workers and you only have one cluster manager try to figure out which worker does what, you are completely bottlenecked by this cluster manager. So So we'll see how this works, but I guess in some cases, of course, it works better than the other, especially when all the tasks are quite different and complicated, which in some sense you have compared to conventional MPI that you usually do very similar things on each MPI rank. Here the task can actually be quite different and different in length, different in number of data, but the Spark will figure out for you. So that's the strength of Spark. So let's go back to Theta. So all these workers and the masters, actually, it's not completely one-to-one mapped to node. You can do whatever mapping you want. So it's better to have a fresh reminder what Theta actually is. So this is actually the Theta compute node. So they will get names at NID, something. So so when you inspect your logs, you need to know these things. So here's you try to connect to these things, and you connect to login node, and once submit jobs through the COBOL jobs manager, and the COBOL job will actually launch your whatever AP run command on the mom node. If you submit a script job, the script will run on the mom node, and any additional AP run will send over your actual, usually MPI jobs over to the compute node. So one thing to remind yourself is that don't try to start any Spark things on the mom node on your script. You have to go through some hoops to do that, to make sure you are actually running on the compute node. And and the script we provide actually does this for you. So Spark Theta, there are many questions, and we're actually actively trying to figure most things out. But as things go, it seems that all the scientific applications are different, and these questions will have answers differ depending on your workload. So first, never run Spark on the mom node, please. And the master, so the question goes like, the master can share, or if you can, you don't really need the master to share with the other slave on one node. The master can have a single node, and of course you may ask how many workers you want to launch per node, and how many executors the workers should launch, and how many tasks per executors, and something we always try to figure out is whether thread affinity in this case is useful. So there's some research going on. I guess some people tried it. It probably provides you 5% to 10% efficient, since the thread does not need to bounce around. But yeah, so these are the things you have to figure out. So I think this talk I will just let's get started, and we'll answer these questions one by one, depending on the your workload of your scientific application. So this Spark job script we provide is under soft data science and Spark job. It's mostly just it's all bash script because I want to minimize the changes that you need to deploy your application on Theta. So since Spark starts with a bunch of bash scripts, it's easier to just interface with it, and so we don't need to change too much things on Spark. So if you're curious, you can go into the RDD file, so which is basically mostly similar to what I'm going to talk here, but it will have more things. And there's also example directory, which gives some files that you can take a look and you may want to use. So currently the script is still under heavy development. just because we are trying to figure out what's the best way to assist user to actually launch a Spark and interact with Spark. And the issues, of course, with Theta is that we have to go through the additional hoop of jumping through different nodes and make sure everything runs well on the compute node. So the only thing we are going to guarantee is that the interface of the submit spark.sh, this is the main bash script you are going to run, would remain the same. So you can rely on, if you always just call the submit spark.sh, your job is supposed to run without any problem. So if you want absolute stability, of course, there's the version number appended. So you can actually use this and use submit spark.h under this directory. Then everything under these will not change. So you won't get anything new also. So the guaranteed interface. So as I said, this is submit spark.sh. It receives some options and your job file and additional argument. So the job file is actually optional. If you don't give it a job file, you will get dropped with a bash shell in one of the compute nodes, which is the master node. So master for the Spark, so you can interact with Spark directly. But otherwise, you can give a PySpark script. So you can give a Java file. You can try the run example, the class, run the Spark provided examples. And you can also run with scripts. In which case, you need to enable script mode. So basically, the script means you start with, you can write your own shell script or whatever Python script, but you have to explicitly call submit Spark submit, sorry. You have to explicitly call Spark submit, the one that's provided by Java, provided by Spark, or you have to interact with Spark by yourself. Of course, it gives you options. The required options is exactly the same as what you would expect from QSub, and some optional options changes behavior. And the Python version is just predefined 2 and 3. You don't need to use this. You can actually use your own modules. For the script to run, there are a bunch of environment variables that you can customize. And you can also interact with the script, so you can inspect what's going on with the environment first. You can programmatically set your things depend on what host it is. So here the example is a Theta, but sometimes it could be Kuli if you run on Kuli. So you can use one single script to control whether to see if it's on Kuli, you do something. If it's on Theta, you do other things. And of course, other things like interactive and the job ID directly inherit the COBOL job ID. And the Py version is just the argument, the script mode. The script dir is the Spark job. In this case, I actually ran on my own instance of the Spark job, which is what I've been developing. So it's under my data science directory. So yeah, so there's output dir is where you actually started, and one most important thing you want to know is probably this Spark master URI and the master host. So the master host is this NID 0383A. So this is one example of what the compute node is. So this is run on one of the compute nodes. So there's something you can customize that you can put in one of the files I will talk about in the next slides. So a couple of things. The Spark Home by default, it uses our installation, which is just the pre-compiled Apache Spark downloaded from their website. It just dropped there. And the Spark conf dir is directly inherited from the object output dir. And there's a working dir and working envs, and you can get more environment variables, and you can just look at that file or source that file from a bash shell. The working dir is everything else will be dumped under the working directory if you don't change it, like the Cobalt output and the Cobalt std-err and std-out. So all these customizable variables you can put in the file called envlocal.sh under your current working directory where you run the Summit Spark. There, first you can set the you can use the Spark job host, like I said, to check what system you are running, and if it's on Theta, if you don't like the default Python, you use module IAM, module load to load a different environment, and you set PySpark Python accordingly, and then the Spark will, if you use PySpark, the Spark will pick up the correct Python. So on Cooley, if you are running interactive Spark jobs, the IPython notebook will be set up through these two variables. So if you don't want that, you just want a usual Python script to run but not spawn IPython notebook, you need to unset that. So conversely, if you are on Theta, these are not actually set, simply because it's people use this script job more. So if you want to get a IPython Spark to start, you need to set these things accordingly like you usually would do. So you can customize the variables in the envlocal.sh with where you can also create this sparkdefaults.conf. We'll go some detail into that, but this will you can put this in the sparkconf dir, which is set in the script. So if in this envlocal.sh, you can use this line to, if this does not exist, you can create this file. So here it's a very simple thing. It's get a Spark task CPU, driver memory, executor memory, and some extra Java options for executor and driver. So yeah, that brings us into the tuning parameters. There are a lot of things you can tune, and most of the things actually has a big impact on your job performance on Theta, simply because the nodes are not really those commodity nodes. It has very different characteristics. So these are the things I generally find useful, but I just give them numbers, and these numbers, make sure you really tune them instead of copy pasting from this. Yeah. So let's go through them one by one. So first, there are 256 cores, and the JVM will understand that 256 cores are 256 cores. And if you don't do anything, it will try to use all the cores, which means that it will eventually spawn 256 tasks if memory allows. This actually never is a good idea for JVM. So, so if you set a Spark task CPU to 4, JVM will assign JVM's idea of 4 cores to your task. So in the end, the maximum number of tasks on one node would be restricted to 64, which is usually a good idea, but depends on what you do, of course. And this applies for PySpark too. So another thing is that the currently we use this simple standalone Spark scheduler cluster manager instead of additional things. So the default is that whatever application gets started, whatever results gets registered, it will just start running. But if you have a scientific application, you have really big data that you realize sometimes, it's just the executor starts slower, and once at the beginning you only have a handful of executors actually doing your job, and you immediately got all kinds of crazy things happening. So sometimes if you really want to get all the resources up and get the Spark running, you need to get a resource ratio to close to 1, I guess, if you actually want to use all the things. And also, if you have a huge number of executors, sometimes the scheduler, the listen of us event queue is not good enough. The predefined is too small. But change it only if you see related warnings. You'll see the warnings in the log file. So there are also a number of network timeout, heartbeat things in the Spark. No other people will break the Spark. So basically, if anything breaks, you can do it over, and probably you don't need high availability too. So what we really want to do seriously is limit the number of network traffic. And we're still trying to figure out why the network traffics have a lot impact on the Spark, but there is. So one thing you absolutely need to change is the driver memory and the executor memory, because there are 196 if you do cache quad gigabyte memory, and you need to increase those to make sure your big data and it actually uses all the memory and give you a benefit. Well, the other thing is Java has, I don't know, 4 or 5 different garbage collector and all kinds of different garbage collector parameters. So this also really depends on your workload. You should set the information out, and you get garbage collection information and tune it during your real workload and try to figure out what best work for you. But probably just want to make sure that GC time does not dominate your whole compute time. So if you want to access the web interface, first you need to find the driver node, which is in this Spark master environment variables. So the one simple thing is just use SSH local forward, because all the compute node does not expose to the public network. So so this is one way to do the SSH jump, going from your local to the Theta, which would be your login node, and the Theta mom 1 is one of the mom nodes you can pick, and your local A0A0 will map to Theta A0, login node A0A0, and subsequently mapped to the NID A0A0. So if you can open this localhost A0A0 from your local machine. Okay, there are, of course, other things to consider. One is the number of partitions for your RDD. Depends on your workload, of course. And there's SSD, so you might want to point your Spark local DLL out there. And the one thing is the dynamic allocation, which is relatively new in Spark, supposed to work fantastically for other people, but you probably want to use all the resources here, so you probably don't need it unless you have a really strong reason you want to run something else at the same time. So there are other things beyond the scope of this presentation, like Shuffle and other cluster managers. If you are interested, try it out yourself and contact us. We're very interested in the Spark usage in all the scientific applications. So all the talks without figures is very boring. So I think, and people actually ask me to show what we can have in terms of performance. So this is some work ongoing with Georgia and Francois here at the LCF. We try to figure out the basic performance characteristic of the RDD. So this is a Scala code on the GitHub. What he's trying to do is basically have a huge vector on an array, which is an RDD. We try to add a constant number and then do an average. So you have an RDD, add a constant number to the RDD, get a new RDD, and the new RDD will get do the reduce. So a very simple map and the reduce. So as your HPC mind kicks in, this is completely memory bandwidth limited operation. And here in this case, I think we have around probably 12 gigabytes of. This array is about 12 gigabytes per node, but in terms of Spark, you never get the exact 12 gigabytes. So it's sometimes more, sometimes less on each node. So you do this, and probably you get if you write very efficient code, you should finish it in probably half a second. So this is what Spark does when we change the number of nodes while keeping the average data per node a constant. It's what we call weak scaling. Here we ran 128, 256, 512, and 124 nodes. So the overall time of this map and reduce is hidden back here, I think one of the black lines. And if I do a count, so if you know Spark, it's a lazy evaluation unless you get a reduce, you don't really do it. It doesn't really actually do that task. So if you insert a count on each stage, you can measure the time in between. But since it will do extra, since it do the extra count, it actually has an extra overhead. So this is what it happens is that each stage almost takes the exact same time, and the time goes up linearly with the number of nodes. If you have a scientific application written in MPI that behaves like this, you will get immediately rejected by our computer readiness criteria. But this is Spark, and this is completely overhead dominated behavior. So it seems, so we're really measuring the overhead. And it looks like we're measuring it quite accurately, such that each stage, all the stages, no matter what you do, whether it's a map or reduce or editing, it takes constant time. And the stage overall is all the time takes to these 4 different stages, and it just looks like 4 times that. So this is what we got, and yes, you can run a large number of nodes on Theta without any problem. The problem is just you have to be reminded that overhead is high. And thank you. just don't panic when you try to tune any Spark things. And any question, please contact me. Thank you.